All right, and we are live. So we are set up. So hi and welcome guys for the SUSE QE Tools workshop. Today, after 1.5 years, we have another topic about SELinux. So already in the March of 2023, there was an introduction by Johannes. So Johannes, thank you for that. And now you're following up with that, but I guess you will also, do a quick refresher, right? So over to you.
Exactly. Yeah, thank you for the introduction. So let me quickly just start by introducing myself because I assume that most of you know me, but maybe not all of you. I mean, it has been 1.5 years, so there's definitely the chance that we have new joiners. So my name is Johannes Segitz. I'm a security engineer working here at SUSE. I live near Nuremberg. I do a bit of code review, mostly lacking time for that nowadays. Product pen testing, so looking at products from an offensive point of view to see if they are actually secure before we ship them. I'm one of the SELinux experts within the company. I used to be the SELinux expert, but fortunately we now have a couple, which makes my life much easier. And I'm the lead of the engineering red team where we do attack simulations against the internal network, although that currently has to take a step back a little bit because we have a lot to do on the SELinux front. So for the outline, I will give you a really quick introduction to the SUSE product security team in case you're not familiar, and then I will do a basic SELinux introduction. And as Oliver already mentioned, so 1.5 years ago, I gave a similar talk. If you are already pretty familiar with SELinux, then that part might not be that interesting for you. But the real reason why I'm here today is that in the second part, I will show you how to debug or report bugs, because that is just something that we've seen that some of the bug reports could improve a little bit. And I think if we discuss that now, then this will likely reduce turnaround times. Good, then let's get started. So later on, if you want to play along, then please have an OpenSUSE Tumbleweed VM ready. You don't have to do this. It's not mandatory. But in general, if you have to work with SELinux from time to time, and probably all of you have to, then it's really helpful to have a VM that you can use for experimentation. Doing that on your host machine is usually a bit dangerous. It's fine if you have access to the machine or can influence the boot parameters, because then you can recover, and I will show you how to do this. But in general, having an SELinux enabled VM is usually a good idea to play around a little bit. And the OpenSUSE Tumbleweed integration is the most advanced one that we have from the SELinux side. Good. So the SUSE product security team. The first important part here really is the product security team, because we used to be the SUSE security team for a long, long time, which proved to be a bit difficult when we got additional security teams. So we have the cybersecurity team that is responsible for the whole infrastructure part. And we have the certifications team, which does the security certifications, or all kind of certifications, but mostly security. And we are the product security team, so we are responsible for the security of our products. And we are split up in two groups. We have reactive security, where we do mainly incident handling. So that's the usual vulnerability workflow that a lot of you are probably familiar with. So security issue is found, CVE gets assigned, then we analyze it, we release a patch for that, and then hopefully everything is fixed. We not only do it for SUSE products, but we also do it for OpenSUSE, which expands the scope quite a bit, because OpenSUSE has a lot more packages than SUSE. So yeah, that's pretty constant stream of work. And then we have proactive security. That's all of the security work that we do before we ship a product. So for example, hardening, code review, all of these things. And there we have to pick our battles, because we have a huge code base. It's not like we are a company with 1 or 2 products where we can go in depth with the code. And we have a couple of mechanisms to actually identify targets for us that promise the most value. This is a comic strip that I personally like a lot. Unfortunately, in the security space, people quite often fail to realize that the awesome finding that they have basically shows a weakness in the work that others did. We really try not to be that way. If you see us acting like that, then please approach us, and yeah, we try to change. Good. So then let's jump into the basics. And before we discuss SELinux, really discuss the basic concepts here quickly. And as said, if you listened to the talk 1.5 years ago, this is probably not that interesting for you because that's a repetition here. The usual form of access control that you see in Linux is called discretionary access control. And we see a typical example here. So we have a file etc shadow, and we see it belongs to the root user, the shadow group, and then we see the access permissions here. The discretionary in the name stands for the fact that the owner of an object can control the access of the object that he owns. So if you are the owner of the file, then you can change access permissions in any shape or form that you like. And that's the normal way that we all know. Has a couple of drawbacks. So first of all, it is pretty coarse. You have a tough time doing really good fine-grained access control there. It's basically these three access bits for reading, writing, and executing. There's a bit more, of course, but that's the stuff that most people use on a day-to-day basis. It's unfortunately pretty prone to user error. Since you as the owner can do whatever you like, you can really do whatever you like. So nothing prevents you from doing something like that. Making your private SSH key read and writable for everyone on the system. Your SSH client will bail on that configuration because it will notice that the permissions are insecure. But if you change the permissions and then don't touch the system for a year, then your key will be sitting there for a year, readable and writable by everyone on the system. That is unfortunately something that can cause issues. Then it's hard to analyze because the information that you need to analyze the security of a system is basically spread over the whole file system. So you need to walk the whole file system, gather all of the information from the disk, and then build up a state of the current system and then try to analyze that. And that is tricky because it's also a race condition. While you gather the information, the system might already change, and then you might be reasoning about a system that is actually not there anymore. And then you have the fact that the root user is basically God, so can do everything. There are capabilities here to split up the power of the root user, but that's not really a good approach to do this because a lot of them are basically root anyway. And it's not like you can meaningfully split up root permissions. It works for port binding and stuff like that, but for other topics it doesn't work. The big advantage is it's familiar, it's easy to use and easy to understand. And that's a big advantage when it comes to security. Especially easy to understand is something that helps a lot. If you don't understand the system, then your chances of making sure that the configuration is secure is basically nil. So that is something that must not be underestimated. And if you worked, for example, in Windows environments with the complex permission sets that they have there, one of the common ways to own a Windows environment is just for looking for misconfigured permissions, because it's so very easy to do in the complex system that they have. So with that, jump to mandatory access control. Mandatory stands for the fact that access control decisions are not made by the owner, but you have a centrally managed policy that contains all of the access rules. That has a couple of advantages. So the centrally managed policy can be managed by people that actually know what they're doing. So in the extreme form, you have something like a system administrator and a security administrator. And the system administrator, for example, takes care of updating packages and everything. And the security administrator is responsible for just taking care of the policy there. You can easily review it because it is just on a central place. So if you take the policy, you know that as long as this policy is loaded, the system is in this state. And usually you also have a better abstraction on which you work. So with the DAC permissions, you have like individual bits. With an SELinux policy, you have higher level statements that already tell you what the intention, at least, of the permission is. You can do very fine-grained access control. So you can do things like compartmentalization, where you say this part of this group is allowed to see that information, but not the other part of the team or whatever. Quite often that's not really necessary, but at least you have the power if you really need it. But of course, almost everything that has advantages comes with drawbacks, so it's harder to understand. It is more complex to administrate. That's kind of self-evidently true because you still have DAC and then you have an additional layer and missing experience, and I hope to address this with this talk. So let's see. Good. The basic idea, and that's one of the main slides that you should probably remember from this talk, is SELinux uses type enforcement. That means that every object on your system has a user, role, a type, a sensitivity, and a category assigned. And if you put this all together, then you get this long string here, and this is usually called a security context. And then SELinux does access control between one security context trying certain operations on another security context. The good news is that for most intended purposes, you can just ignore everything and only concentrate on the type. The type by default has a suffix of _t. That's not necessarily true, but most of the time it's true. And as said, if you see a security context like that, forget everything else, concentrate on the type. In 99% of cases, that will be enough to understand the problem. So the other thing that you please should remember is a capital Z. That is the command line flag that you use on a lot of tools to either show information about SELinux or make the tool do the right thing on an SELinux enabled system. And we see a couple of examples of that later. So pretty much everything on a system has a security context. We see an obvious example here with a file. So again, we list the etc shadow file, but this time we add the magic capital Z flag. And we see that on this system, etc shadow belongs to root and to root group. And then we see the security context. And again, we ignore everything apart from the type. And we see the shadow file has the type shadow T. That highlights one thing that you see in a lot of cases on an SELinux system. You should see a pretty good correspondence between the object you're trying to analyze and the type. That's not 100% true. So it's not like you always have the type name just being the file name just with an _t added to it. But if you see a massive discrepancy here, so if you see etc shadow tagged as temp file T or something like that, then something obviously went wrong. You also have that for processes. So if you list the process again at the capital Z, and here we grab for the postfix master, then we see the postfix master has the type postfix master T. So that again seems very sane. You really have that for a lot of objects on your system. So you can have a security context on sockets, on packets. There are over 130 different security classes in the SELinux policy that we currently ship. So there's a lot of things that you can control with SELinux, but in the most cases, you can just concentrate on files and processes. So that should be enough for a lot of the work that you do with SELinux. So when an access comes in and is controlled by the system, then first you go through DAC. So the default Linux permissions that you've all been using for a long time get checked first. And only if the permission is granted via DAC, then SELinux comes into play. And SELinux is a deny by default system, so it's similar to a well-configured firewall where you say you only have allow rules for the stuff that you want to allow. Everything that you want to deny, you just don't have an you don't have a deny rule for that. You just don't have an allow rule for that. And it is a little bit like a firewall for system calls. So especially for some workloads, you have a really good correspondence between the system calls that you see and the permissions that you need. So if your process tries to read a file somewhere on the disk, then you will see a read permission on file objects. If it tries to open a file, you will see an open permission. So especially like for file access, that's pretty good one-to-one correspondence, but also in many other cases, that's pretty similar at least. Good. I will now show you really quickly an SELinux module, and the reason why I want to show you this is that later on I will tell you about Audit to Allow, which is a tool to help you fix policy problems. And this tool can show or can use some of these interfaces, and then it's good to at least have seen this one so they get a certain understanding of that. So first you start with the name of the module and the version. And then this is a very common pattern that you almost always see. You have an executable type, so arpwatch exect. This will be the type that will be used for the files on disk. And then you have a type that corresponds to the name of the daemon, so arpwatch t. And then we tell the policy via something like a function call. So as Linux lingo, it's called an interface. We tell the system that files of arpwatch exect, if they are executed by the init daemon, then please transition to arpwatch t. And that is a, of course, common pattern. So you have the init system running, it starts a daemon, it executes a certain file on the disk. The file needs to have the proper label attached, the proper security context attached. And then the system knows, okay, I want to transition this process into this domain type, so into this security context. And you pretty much see that with every daemon. A lot of daemons use different files, and with SELinux, you usually want to give them different types. So, for example, here Arpwatch has data files, and so we define our own type for the data files for Arpwatch. And then we tell the policy, well, this is a file type, so that other daemons, other functionality on the system that, for example, needs to read arbitrary files, knows how to do that via the use of interfaces again. Usually you have a couple of different files. So for example, Arpwatch also has these PID files, and then there are different interfaces for that. So we see the executable type is something that is very important to move to the right domain, to the right process type later on. And quite often when you see problems in QA, when you see some denials, then a good thing to check first is if the labeling of the executable file is actually correct. Because if the executable file is not labeled with the correct label, then all of that can't work from the beginning. And this is like one of the low-hanging fruits that you probably will encounter from time to time. Good. So we've seen an example for the rules that specify how the SELinux policy module is built in general. But we also need to label the file system. So if you have a non-SELinux enabled system, then you will not have these labels on the file system. And you need to get to a point where you have these labels on the file system. And to do that, there are also rules specified in the SELinux module that will tell you how to do the initial context. So you have a one-time labeling operation that will label the whole file system. And only during this initial labeling, these rules are used. And this is really important to understand because in my experience, that's very easy to misunderstand for SELinux newbies. It's not like the system is checking these rules constantly while it's running. It's really only doing the relabel operation where you say, here's a file system, please adjust all of the labels. Then during production run, the policy itself specifies which labels will be used when a certain process with a certain security context creates a file somewhere. The format here is rather simple. You just have a regular expression. So in the most simple case, in the first line, you just specify the path directly, but you can specify arbitrary regular expressions as you see in the next two lines. Then you have a specifier in the second field that specifies, is that only valid for regular files, for socket files, for directories. You can also just leave it out, then it's valid for all types. And then you have a security context wrapped in this interface call here. And the most important point again here is just the type. So we see the Arpwatch binary that is executed gets the type Arpwatch exec t. That's what I just mentioned previously. So The tool RestoreCon is the tool that you can use interactively to check your system. We will see an example for that later on. So if you have an SELinux enabled system, sooner or later something will not work. And that then might be an SELinux problem. And if it's a SELinux problem, then very likely you will see an SELinux denial. And they are usually in the audit log if you have an audit daemon running, which should be the case on pretty much every system. They have type AVC, so you can search for that, and we will see examples for that later. And it's a pretty long string. I broke it up a little bit here. So first in the curly brackets, you see what kind of permission was tried. So something tried to transition. Then we see a bit of context here. So it had to do something with SSHD and the shell was involved. And then we see the most important parts here, namely the source context and the target context. And again, we ignore everything apart from the type. So we see that kernel T tried to transition to unconfined T. No? This is what is contained in this SELinux denial. Reading those takes a bit of practice, and it's not really the goal for today's training or in general for people that are new to SELinux to fully understand all of these denials right from the beginning. The most important part is really first to be able to parse it in general, so to understand which are the important parts here. And also, and I will mention that later again, we need these denials. So if we want to fix anything on the policy, then we always need the denials. Without the denials, it's going to be really rough for us to identify any problems. Good. I will now change an OpenSUSE Tumbleweed installation to use SELinux. So if you want to play along, then please boot the machine. I will set my slides now to the left side, and I will have a terminal on my slides to the right side, and I will have a terminal on the left side. Are you able to read the font here? So is that okay?
Yeah, that's good.
Okay, good. So then let me jump to the next slide. Here are the commands that I will now be running. I can quickly just paste them also into chat in case you don't have the slides yet, but also the link to the slides if you want to download them. So the first call is just to install all of the necessary packages. And by now there's also a pattern that you can use for that, but I'm a bit old school here, still use the individual packages here. So first we install an SELinux policy and we choose the targeted policy. There are a couple of policies that are available, but the targeted policy is the default policy and it's also the one that you should use. Then we install the policy core utils and the SE tools console. So these are all of the tools that we will be using in the further steps here. It allows you to administrate your SELinux installation. And the SELinux auto relabel package is a nice one. It recently changed, and yesterday I actually had to fix a bug while preparing all of this. Let's see if it's already in factory or if we have to fix it now on our own. That allows you to automatically relabel the system. So after installation, we now installed everything. We should have either in the root directly or in the directory SELinux. Should use the proper command. A file called auto-relabel. And if this file is present either in the root directory or in etc SELinux, then the system will know that on the next reboot, it should automatically relabel the system. And now let me check. I fear that probably the SELinux auto relabel package still is in the broken version, so we need to do this a little bit differently. Usually we would set the system to enforcing right away. You can either do that with the set statement here. So if we look at the SELinux configuration file, we see by default it is permissive. So that means that SELinux will show you what is wrong, but will not enforce it. And usually we would set it to enforcing right away. But since SELinux auto-relabel probably still is broken and did not get the fix that I submitted yesterday, it will take a little bit. and we will keep it in permissive for now and then only set it to enforcing later on. With the next command, we just adjust the etc default grub configuration file. You can also do that by hand. What we do here is that we add security equals SELinux and SELinux equals 1. You can also remove the security equals AppArmor, but the second setting will override it anyway. And then we
What is the
update.
meaning of the two different? So SELinux equals 1 sounds kind of redundant when you Linux.
Yeah, the difference is that security equals SELinux just tells the system, please use SELinux as your main mandatory access control system. And then SELinux equals 1 means really enable SELinux. So you can have your system configured for SELinux and not have it running.
I see.
For most people, it doesn't make a lot of sense. Then we update the bootloader to make sure that these settings are actually there. And then something that you don't want to do on production systems, but which is fine here on this test system, is delete the audit log, because you might have AVC entries that are coming from AppArmor or just a lot of stuff collected on there. So if this is a fresh installation and you don't care about the system, just delete the audit log. That will make it easier to actually see what we're doing later on. And then we will reboot the system. If we would have changed the system to enforcing, and if SELinux auto-relabel already received a fix, then we would come back to a system that now has SELinux enabled in enforcing mode directly. But since we can't do this now, we have to do one manual step. So let's see if the system is already back. It is already back, and I will move one step ahead, which usually would not be necessary, but since we have that bug now, let me already show you the SE status command. This is the command that shows you on an SELinux enabled system how your system is configured. So we see SELinux itself is enabled. We currently run the targeted policy. We are currently in permissive mode, and the configuration file set us also to permissive mode. And now we need to do manually what the system would do automatically if SELinux auto-relabel would not be broken. We have to relabel the whole system, and that's done with the restore con command. So we just tell it to recursively go over the whole system and relabel the system. And what you see here now is the reason why the first boot on an SELinux enabled system can take a while, because what is done now is taking all of these rules that I showed you earlier, all of these regular expressions, and checking them against the file system, and then labeling the file system accordingly. So this can take a little bit. It depends on the size of your system, the speed of the underlying storage and everything. Especially if you have a really, really big storage system in the background, then that can unfortunately take a while. And since this is usually done during first boot, that can be a bit confusing for
So
people.
that's really setting the metadata on all directories, or it's also files.
On everything that is on the file system. So
Yeah.
directory files, symlinks, sockets, everything. Let me quickly go here into the system. Maybe we can still see something that's not labeled. Yeah, perfect. So here I'm still running the restore con. And now I listed the root directory and added the capital flag set again. And we see that, for example, the home directory is still not labeled, and therefore it receives the default label unlabeled T. The etc directory is already labeled, so it already has the proper type. And I'm wondering a bit why it's that slow, because usually on a smaller VM that should return quickly, but I assume it also takes a while at your side, so let's just wait for it. Any questions now to this point? Yeah, perfect. Good. Then now let's change the SELinux configuration. You can either use this set command here to change it, or you edit the configuration file directly. And now let's set it to enforcing. Let's delete the audit log again to start with a clean slate. And now if we reboot, we should come to a fully enforcing system. And there we are. Perfect. Okay. Now we are in an enforcing SELinux system, and as mentioned, so as soon as this fix for SELinux auto relabel is done, you can just do this in one step, and this in-between step of booting into a permissive system and manually relabeling is not necessary anymore. So I already showed you the SEStatus command. Let's run this again. Now we see we are actually in enforcing mode. Everything else stayed the same. When you look at the processes and add the capital Z, you will see the security context that I mentioned earlier. Usually when you do this, you will see a couple of processes that get, or a couple of security contexts that get repeated a lot. So it can be helpful to just remove everything that runs with unconfined T, because that will be the user processes that users spawn, at least by default. And then it might make sense to just remove the kernel processes. Because if you run the command like that, let me quickly just change the screen here. Then you see only the processes that are not unconfined or not the kernel itself. And then you should see a really good correspondence on a properly labeled system between the daemons that are running and the types that you see here. So NSCD is running in type NSCD-T. Network manager is running in type network manager T. Same for cups. So it's not always perfect, but usually on a well-configured system, you would like to see a pretty good correspondence between all of this here. One thing that's a bit different here is there's the domain currently running as unconfined service T, which is a fallback type. So all of these daemons that you see running above have a specific executable type that causes them to end up in the domain that you see here. But if the init daemon executes something that does not have a specific executable type, then there's this fallback type here. So if we list this file here, again with the capital Z, we see it's just marked as bin T. So there is no specific type for that. And that means that this service will just run as unconfined service. It's a pretty neat fallback because that means that daemons for which you don't have a profile will still run properly in most cases. So since we already did the relabeling, we've seen that a bit before, but now if I list the directory again, the root directory again, I see that everything has been properly labeled. Again, you have a really good correspondence between the directory that you see and the type. There are just two things, or one thing that might be a bit confusing in the beginning. So the home directory has the type home root T, and the root home directory has the type admin home T. And home root T, of course, sounds a little bit like the type for the root home directory, but it just means this is the type for the home directory root. It does not have to do anything with the root user. Might be a bit confusing at times. If you dive down into the directory hierarchy, then you see more specific types. So for example, here we see that SNMPD has type directly in var. So the types become more specific the deeper you go. Then we've seen already the use of restorecon that allows you to label the file system again according to the rules that are set in the policy. It has a very nifty mode here. With -v, you specify verbose mode, and with -n, you tell it to not actually change anything. And that's a pretty good idea when you do some debugging on a system, to not change it, because first you want to understand what label changes would have happened. Otherwise, especially if you want to recreate a problem, it might get annoying to then restore it back to the broken labels. So now we check the file system, but since we are on a freshly labeled system, nothing really happens here. Everything is properly labeled. And if you remove the -n, then it would relabel all of that that you've seen now, but nothing to relabel here on the system. If you want to check your identity, you can also specify capital Z again, then you see your own security context. So at the moment we are running as unconfined T, and I will mention that a little bit later when we discuss the various ways of managing your SELinux installation. If you want to check denials, I mentioned that they are in the audit log. I personally just use grep a lot for that. So you can grep for AVC in the audit log. At the moment, we don't have an SELinux denial in here. The proper way is to use these or search commands, which allows you to properly search the audit log. Then you have to specify AVC, user AVC, and SELinux errors. They usually also want to see the errors themselves. If you have to do more complex debugging or have a large audit log, then it might make sense to use or search. But I usually just use a lot of grep, and also this tail command is rather helpful for in my mind. So if you tail the audit log and then grep for AVCs and work on a different terminal to debug your problem, then you see the AVCs coming in here exactly as you work on the other terminal. You might have a little bit of delay because of buffering, but in the end, most of the time you have a pretty good correspondence between what you do and what you see in the denials here. And for me, at least, that's very helpful when doing some debugging. Good. The SEManage command allows you to manage your SELinux installation. It has a couple of sub commands. I will show you a couple of those. It's one of the key commands to know when you work on an SELinux enabled system. So I mentioned earlier that we are running as unconfined at the moment. This is something that the SEManage login subcommand configures. So on a default system, you have this default mapping set to unconfined U and a specific setting for the root user to unconfined U. And that means that on this system, all of the users will be running as unconfined T. That is a pretty good setting if you don't want to break a lot of things. Of course, for security reasons, there are stricter settings within a Linux installation. But this is something that I will cover in more advanced trainings, and also which is not something that we have in our configuration. So you should not really see it in testing here. What you might see and what we've seen breaking OpenQA tests from time to time, especially now that we try to set tumbleweed to enforcing by default, is these port mappings. So with the subcommand port and -l, you can list all of the port mappings that exist on the system. And it's a rather long list. You can just search for it, or again, use my beloved grep. And if we grep for SSH, then we see that there is a definition here for SSH port. And it says that it must be a TCP port and port 22. Now, if you configure your SSH daemon to use a different port, then this will not work on an SELinux enabled system, because SELinux says, well, this domain is only allowed to use port 22. So for all of these daemons here, or for all of these configurations that you see here, if you change the port in the config file, you also need to tell your SELinux installation about that. And the SEManage port command allows you to do that, either to define an additional port or just change the port there. And this is something that we've seen in OpenQA go wrong. So if you have a test there that uses a custom port, then you will very likely need to adjust it on everything that uses SELinux, so everything that is based on SLFO, SLImicro, and going forward also on Tumbleweed, to tell the SELinux installation about this port, or maybe not use this custom port. As mentioned earlier, the rules to initially label the system are a pretty important aspect of an SELinux installation. You can manage those with the SEManage f context command. The easiest one is just the subcommand -l, where you just list all of the rules that are here. And again, you can just query via the command itself, or you grab again and let's see all of the rules that we have for SSH on the system. So there we see like some of the more obvious things like the SSH binary itself or the daemon binary itself, but you also see rather specific rules that are related to other software. So usually you have a rather long list of these, and you can also change them. So if your system is specific in a certain way, let's say your SSH daemon lives in user local, whatever, then you can configure this here. Then there are booleans, which are settings on a Linux system that you can toggle on the fly to change the behavior of the system. The canonical example here is this HTTPD enable home doors. So you might have worked on systems where there's a web server configured to serve files from your home directory out to the public. So for example, if you log into Wotan, then there are directories, I think public HTML and export, and depending on which directory you use, it will show up on a different web server. That also means that the web server needs to have the permission to access your home directory. And usually on most systems, you don't want this. So if you don't have that special configuration, then you don't want the web server to have anything to do with your home directory, because this is probably something you actually want to protect from the web server. But if you have that use case, then you still have to do this. And then you just turn one of these booleans to active. And there are a couple of them. So with -l, you can list them again. These are all ways to change the way how SELinux works on your system on the fly without having to change the policy itself directly. If you want to activate something like that, you specify -m to modify it, then --on to turn the boolean on, and then just the name. And once we run this, now the web server would be able to access the home directories on the system. So how do you debug SELinux problems? The first step that you need to make absolutely sure is if it's really an SELinux problem. And the easiest way to actually determine this is to set the system to permissive mode. So we've seen the configuration file. That's one way to do that. But if you want to do that on the fly, then you have the set enforce command that allows you to change the state. So if I run set enforce 0 and run SE status again, then I see at the moment we are running in permissive mode, while in the configuration file we are still set to enforcing. Running set enforce 1 brings me back into enforcing mode, so you can toggle during runtime if you are in permissive mode or not.
Johannes, I have one question. You said how to debug SELinux problems. I guess for most people, SELinux problems would manifest as in preventing them to do something. That what you mean with SELinux problems, or you're thinking about unexpected behavior of SELinux itself?
Basically any problem you have with SELinux, especially now here when it comes to enforcing. So in the most case, it will mean that something goes wrong on your computer and you can't really explain why.
Like a permission denied error.
Yeah, so permission denied error is like the good case, because there you already get the hint that it might be related to permissions. It might just be that something suddenly does not work anymore and you don't get any meaningful error, because the daemon can't really understand why it's not able to do anything anymore, because it is denied by SELinux without really without really communicating to the process, or the error code that might be returned might not fully express what the current problem is.
Okay, wouldn't a more secure way to debug that to first take a look into the audit log to see if the application which is misbehaving is maybe showing up or none of that?
We will do that right in the next step. The thing is, in the beginning, you usually want to. So first of all, I'm always talking about test systems here.
Yeah. Okay.
So,
okay. Then I agree.
yeah. I mean, the next line, and that's actually something that I want to mention here, is So this is a global state. That means that your whole system is now in permissive mode, and that is suboptimal. That might be okay on a test system, but as soon as you are not in a test environment anymore, you usually want to do something more specific. So the SEManage command allows you also to set only a certain type to permissive. So let's see, you're seeing some problems with Kiwi. Then if you run this command here, now the type that is used for Kiwi will be in permissive mode, while the remaining system still is in enforcing mode. So good comment. It is definitely something to have in mind that you reduce the system security if you set it to permissive globally. So let's say you set it to permissive and the problem goes away, then you have a strong indication that it is SELinux. It's still not 100%, but very likely you then have found a culprit in SELinux. So what do you do next then? The next thing that you would do is search for already open bugs. You can either first check for the AVCs if you are familiar with them, maybe after this training. But usually also if you just enter the name of the daemon and SELinux, then you should already find something in our Bugzilla. Another good way to see if we are already aware of that is this URL. So this is our queue where we list all of the bugs that we're currently working on. We have an open section there of all of the bugs that are currently not assigned. We have a best effort section for the stuff that we want to do if we find the time. And then we have individual people assigned with their own queue. So if you find something new, then it would make a lot of sense to check in here if you find something that sounds very similar to what you've been seeing before. Then next step, make sure that you actually run an image that has the recent policy fixes, because we've seen that many times that people identify a problem, report it to us, then after a while try to check if the problem still persists, and we in the meantime release the policy update, but the policy update is not yet in the image that they're using for testing. And our versioning scheme is really simple. It's just a timestamp that comes directly after SELinux policy. So please check your images if you see that you have a recent policy in there. If it's still the old policy version, then you will likely see the same problem. You can also check with SE Search, and I will show that on the next slide, or you can just ask us. So if you are in doubt, then please first verify that you actually have the fixed version. We've seen that more than once, that people just spend a lot of time testing with the old version. So if you have a rather simple fix and you see that a certain type, for example, does not have the proper permissions, then you can also use the SE search command to search on the system for the permissions. SE search allows you to query the SELinux policy for all different information. And one way that can be helpful in simpler cases is this command here. So you search for a certain type. Let's say you saw some problems with the executable binary for Kiwi. It was missing some permission. Then -AT is something that you pretty much always specify when using SE search. It specifies that you want to see all of the allow rules and the conditional rules here. And then with -ds and -dt, you limit it actually just to KeyVT and not do a more extended search on attributes. And if you run this, then you will see the output like that here. And then you will see certain permissions. And let's see, the execute permission was missing for some reason in the previous update. So if you know that exactly, you can use SE search to check if the current policy supports something like that. Very commonly, you just have a labeling problem. So something is labeled wrong on the system. And there you need to differentiate between the current state and the intended state. The current state is what you see when you add a capital Z and list something. So let's take the example that we used previously, list the shadow file here. So we see the shadow file has the type shadow T. And then with the SEmanage fcontext command, you see the state that is actually configured in the policy. So again, let's just grab for shadow. We see that the shadow file also in the policy has the proper type. So if you have a labeling problem, then these two commands can be used to see if the fix that would be in the policy is actually already applied to the system and if the policy already has the proper labeling rules. If you see problems and they don't, or they go away when you go to permissive mode, but you don't see any AVCs, that can happen from time to time because there's something called don't audit rules in the SELinux policy. As mentioned previously, the SELinux policy is a deny by default system, so it will by default not allow anything where you don't have a rule for it. But sometimes you want to deny something and don't want to see the AVCs for it constantly. So let's say a daemon has two code paths. First, it tries a certain privileged operation, and if this doesn't work, it then falls back to an unprivileged operation. And sometimes daemons do that, and the policy maintainer decided, well, it should just not use the privileged operation. Then if you don't allow the privileged operation, the daemon will still work, but you will see these denials every time you start the daemon. So then you add a don't audit rule that tells the system still don't allow this, but also don't log it. Sometimes you run into problems where something that is don't audited actually causes the problems. That's not that common, but it happens from time to time. And if you see something like that where you just don't see any denials and you're pretty sure it's still SELinux, then you can, with the SE module command, rebuild the policy on the fly. It will now remove all of the don't audit rules. So starting from now, you will also see the denials that are in don't audit rules. So you restart your test case, and if you now see denials, then you know, okay, this was the problem. You also need to remember to just go back and add the don't audit rules afterwards, because otherwise you will see a lot of denials that have nothing to do with your problem. In general, search engines and bug trackers are your friends. So if you look at the AVC and you remove all of the specific information, so there's a timestamp in there, there are PIDs in there, sometimes path information. If you remove all of that and just enter it into a search engine or into our bug tracker, then very likely you will find a similar problem or maybe the exact same problem. So we follow Red Hat as upstream for the policy development. So it is quite common that, for example, in their bug tracker, there's already some information about that. So if you want to report a bug, if you are sure it's an SELinux bug and you want to report it, then in the wiki, we have a guideline on how to do this. You can just go to the OpenSUSE wiki and search for SELinux, then you should easily find that URL. Most important points here are, please provide always the SELinux status. So we need to know the state of the system. We need to know the operating system version. We need to know the policy version so that we know if the fix is already in there. And we need the SELinux denials. So you can get this with search or the grep commands that I use. And the most important part here is we don't want to see the output of SE alert. So we will see that on the next slide in a bit more detail, why we really want to see the AVCs themselves, not the SAlert logs. And then, of course, we need to know the software that is actually causing issues, hopefully also the version. Really important how we can actually reproduce this. Because with SELinux problems, quite often we need a way to debug this locally before we can figure out what the fix is. So please provide reproduction steps if possible.
All right. Johannes, we should reserve like 2 minutes for questions. And if there's sufficient interest or if you have more content that you would like to share in a live session, you can consider to come up with another session. I would like to take a look on the time. Okay.
Just have this one slide. So if you
Sure.
let me finish this one, then we are done. So this is an example of why we actually need the AVC. So this is something that we've seen in a lot of bug reports because this SE troubleshoot daemon runs. And this is what you then see when testing or looking at the logs. And the problem is that there all of the technical information is missing here. So we don't see the source context, we don't see the target context. It is contained a little bit here in the text itself, but the information actually would only come out if you run this SELert command. So please provide the proper AVC directly. And with that, we skip the order to allow part and are ready for questions.
Thank you. There was a question from Dimstar now about well, it actually tailored to, but maybe you can also comment on that. Can we get those details in OpenK as part of the fail hook? Because the SELinux debugging, like gathering information, is already part of OpenK test, right?
Yes. So to some extent, we have that already in the OpenQA runs. There is already some functionality to gather all of the logs. And if the audit log is in there, then quite often we have the necessary information in the OpenQA run. It is unfortunately missing from time to time in the bug reports themselves. And that just makes the sorting of the bugs a bit tricky for us. So please already include it into the bug report. Also because during an OpenQA run, you might see multiple SELinux problems, and then it might get easy to confuse the bugs if we don't have the technical information about which individual problem is now handled in this bug.
Right. Any question from the audience, to be honest? Then I have a question. Johannes, how helpful do you consider the SELinux covering in OpenK test?
So the OpenQA coverage for the SELinux functionality itself is okay, I would say, maybe a bit basic, but okay. The real value here that we currently see is just the OpenQA test framework in general, because we now switched an SELinux Tumbleweed installation to SELinux.
Yep.
And of course, now tests are breaking left and right, and to some extent, these are test problems. But we also see real SELinux problems because the interesting part really is to test the real functionality, and OpenQA.
Right. Yeah. Okay. Cool. That's what I wanted to hear. So, any other comment by anyone? Seem like it. So, nope, we are good. So, guys, the just a short announcement. The next workshop falls on the 1st of November, which is a public holiday in some places of yours, including here. So we will skip that session. The next one is on the 15th of November, and it doesn't have a topic yet. So if you're interested, then please suggest a topic. Be happy to. And goodbye.